going to do hopefully 2 sections today. I've just a number of questions to try and see if we can fit it in without hopefully changing too much. So first one is how to find double integrals by changing the double integral from XY coordinate system to polar. This is essentially the generalized rule for doing that. So you've got any double integral you could think of, double integral over some region D of a function f of xy dx dy. You can rewrite it in this polar form. It's basically you find the limits of integration of the region D, but in terms of polar. The x's in your function become r cos thetas. The y in your functions become r sine theta. And then you have this extra r dr d theta. Now, in polar, x's is this guy, as you can see. Y is this guy. And dx dy, or sometimes it'll be dy by dx, is replaced by this guy. So that's basically the 3 pieces repeated here. Now, there are some polar combinations that come out really nicely. For instance, x squared plus y squared ends up being r squared. Another very nice one is that the square root of x squared plus y squared ends up just being r. So those are quite useful, quite common identities where x and y are connected. As you can see in these cases, both of them to r squared and r. Anytime you see an x, turn it into that. Anytime you see a y, turn it into that. And we are good to go. So, I got this guy set up somewhere. I do. First question is really just getting you to set up what that double integral would look like. So here we've got a double integral, pretty general. It's made up of basically an inner circle and an outer circle. So when you're trying to think of how to describe this region in terms of polar, you imagine you've got a point at the origin and you just draw what are called the radial lines. And R represents, the values of R represent the region you're talking about. So if I went along here, I would start at a radius of 8 and finish at 10. So that tells me that R is going to be from 0 to 10, or sorry, from 8 to 10. And then in this particular case, since it's the entire circle, you imagine that you start at the XY axis and then you just rotate it until you build the shape. So in this particular combination, theta would be 0 to 2 pi, no, complete circle. And the R would start at 8 and then finish at 10. So we just need to find somebody who does that. And I believe it's that one. That would be the end of the question. It's really just a warm-up question. So, question 2, or at least one like it. We're going to do the double integral of a region D. The function is x squared y dA. And then the region D is described as the top half of a circle radius. So it's the top half of a disk, which is essentially a circle, with the center of the origin, which they all will have, and the radius of 5. Okay, so let's see how we would set up that double integral and change it from x's and y's, which is essentially what it is. Well, if you draw what the region D looks like, it's the top half of a disk, which I'm calling a circle, and its radius is 5. So it would be that region there. Well, in terms of x and y, at least that's what it would look like. If you try to describe this region using x's and y's, it would be really ugly math. The x's would be okay, -5 to 5, but the y's would be from 0 to the square root of 25 minus x squared. That would not be fun. So instead, we're going to turn it into its polar functions. If I do just a general radial line, this shape fills in from r equals 0 and it finishes at 5. So I can tell, I can tell that my R is from 0 to 5. Now theta, well, you imagine, I don't know if that's going to work. Just a little pen. Right. Oh, maybe this. Maybe this. So you imagine you're starting off on the x-axis, and then you rotate the shape, and theta goes from 0, which is here, and you end up over here, which is 180 degrees, but everything is in radians, so 0 to pi. So that's pretty much what you should do as your first step. Draw the region they're talking about, because I think it's easier if you can visualize what piece of a circle it is. When you do polar coordinates, it's a very niche market. You should probably only want to use it when the region D is part of or a piece of something to do with a circle. So our new guy is going to be the integral from r equals 0 to r equals 5, and theta equals 0 to theta equals pi. Our function was x squared y dA. X is r cos theta, so x squared is that guy. Y is r sin theta, right, from here and here. And then the dA, which is essentially dx dy, gets replaced by that extra r. And in the way I'm doing this, it looks like it's a theta first, and then it's an r second. And at this point here, what I would do next is to try and make it a little bit prettier. If you square this guy, you get r squared cos squared theta times r sin theta times r d theta dr. And I collect all the pieces together, they'll get that one, that one, that one, so that's r to the 4. And then I've got these two guys, so that's a cos squared theta, a sin theta, a d theta, and a dr. So at this point here, basically, I've converted the original integral into its equivalent polar. Now, what we need to do is look at the easiest way to evaluate that integral. Well, there are a couple of really good things that are going on here. The fact that these two limits of integration are numbers doesn't that mean that we could switch them around if we wanted to. But more important than that, isn't this separable? You see it? R to the 4 times some stuff. And separable is good. So we have r equals 0 to r equals 5, r to the 4, dr, times theta equals 0 to theta equals pi, cos squared theta times sin theta, d theta. Typically, these questions, there are a great chance anyway that these are going to be variable separable. That's good, right? It does mean your workload's a little bit less hassle. Also, if it does separate, this guy here is probably just going to be a power rule, right? It's going to be r cubed, 4r squared. You might get an r to the half occasionally, but it's pretty much power rule all the way. On the other hand, this guy over here, right? See this guy here? He is probably going to be, the way these things are constructed, isn't this probably going to be combinations of various powers of sine and cosine? And that means that we have to be a little bit more work there, because they're going to be harder to do. And we're going to have to look at how do you integrate combinations of sine and cosine, as we have here. So I'm going to break this into two separate pieces. I'm going to do this one first. that guy there is 1/5 r to the 5, the power rule, evaluated at 0 and evaluated at 5. If you plug in 5 here, you get 625, and if you plug in 0, you get 0. And so the answer is 625. And if any of you are amazed, it's not that the answer's in, I'm writing it down. It's actually that calculation's easy to do, because 5 to the power of 5 cancels one of them. And so this is 5 to the power of 4. And 5 to the power of 4 is just 25 times 25, which is what 625 is. On the other hand, this guy, he's going to cause some issues. And there isn't just one situation. When you get these guys, there are various techniques. One of the most common is going to be a use-up, which is what this one is. But that's not the only thing. Sometimes you have to do using identities to change the way it looks to allow you to integrate it. So by changing the identities, I mean things like cos squared ends up turning into 1 minus sine squared. Also mean cos squared might turn into a half 1 plus cosine 2 theta, right? You get what you get. In this one, we got lucky. It's actually not that bad. It's a u-sub. But when you've got a u-sub, you have to decide, is it sine theta or cosine theta? It's never going to be cos cubed or cos squared or sine cubed. The u-subs, when you do them with these, is a single sine theta or a single cosine theta. Which one is it in this question?
Well, I think you'd want to get rid of your cos squared. So you probably want to make cosine, right?
That's the right one. Yeah.
Because you're going to get the derivative of that as sine.
Nailed it. That's exactly what you do. Right. And when you figure that out, that's great. Now, since there's only two choices, I guess I might screw up sometimes. Not that I ever do, but if I did screw up, wouldn't I find out that my u-sub didn't work and I just cross it out and I do the other u-sub? I mean, you've only got two choices, so you're going to get the right one eventually. But it's better if you can predict, saves you having to, spend time doing the wrong one before you can find the right one. And your idea, John, of the cosine is going to get rid of that sine when you differentiate it is a good way to look at these. Well, we'll finish this in a minute, but here's some combinations. Sometimes you're going to get a power in both of them, right? You're going to get a cos cubed and a sine 5, something like that. If you have a cos cubed and a sine 5, always pick the bigger power as your u-sub. It's still going to be sine theta, right? And if one of them is odd and one of them is even, which that can happen as well, you should always pick the odd one as your substitution. So if you get a cos to the 4 and a sine cubed, something like that. Sorry, I said that the wrong way. Cos to the 4 sine theta, pick the cosine 4. Pick the even one. Right. So back to this guy. Differentiate with respect to theta. We'll differentiate a cosine. You get a negative sign. Do the crossover. Divide both sides by negative sine theta. And we will isolate the du. So we have the integral of cos squared, which is that guy, times a sine theta, and replace the sine by 1 over negative sine theta du. And that guy gets us, well, actually, that's all you get. It's actually a very nice answer, isn't it? Just negative u squared. Right, the signs cancel. Oh, negative floating around. Power rule.
Did I hear you correctly? If you have an odd and an even, pick
the even.
Even, okay.
Pick the even. If you have two odds, pick the biggest odd. And if you have an odd and an even, pick the even. If you've got two even, swear profusely, because they are ugly, ugly. And they are totally different. They are not U subs. They are just totally different. So we may or may not get that situation. And if you want to know what to do with an even, look it up. There are, I'm sure you could find an example somewhere. Basically, you have to turn the sine squared into a half, 1 minus cosine 2 theta, and you have to turn the cos squared into 1/2, 1 plus cosine 2 theta, and oh god, a sine squared cos squared is probably the only one that you would expect to be able to do. If you do it a sine 4 and a cosine 4, you'd be there for a day. The math is just so messy. Right, so add 1 to the power, divide by the new power, looking good. Replace it back into thetas. And then at this point, you can then do theta equals 0 to theta equals pi. And what does that get me? It gets me negative 1/3 cos cubed pi. Take away negative 1/3 cos cubed 0. Okay, cosine of pi is nothing, so that guy's 0. Take away a negative is going to be a plus, and cos of 0 is 0, so basically plus 1/3, and that means that this guy is 1/3. So our answer is going to be this fella, 625, times the area of this fella, which ends up just being 1/3. And so that's 625 thirds. And I'm now going to go over and check my answer. The right answer is double that. So where did I screw up? Evidently this here is 2/3. Okay. Cosine of pi is not 0, guys. What number is the cosine of pi? Cosine of pi upon 2 is 0, but what's the cosine of pi?
-1.
Okay, so 2 negatives make it a plus. So guess what? You get 2/3. Now we get the right answer. You were talking earlier about, John, where you do all the hard work and then you do one mistake and the answer fails. That would be a classic example of that, right? I would have put in 625 thirds and it would have said wrong. Right? And it was simply just, careless. Cosine of pi is not 0. Cosine of pi upon 2 is 0. The sine of pi is 0, but that's not what I was evaluating either. Okay, we like that guy? Now we finished? Right. Every one of the ones that I'm going to be doing with a little give and take is pretty much going to follow the same format that this one is. I'm going to draw a picture. I'm going to find the limits of integration of r and theta. I'm going to take this guy and convert everybody into r's and thetas. And then I'm going to make it look pretty. And if I'm lucky, I'll be able to split it. And if I'm not lucky, then we just integrate it in the order it's in, and that's fine too. And hopefully at the end, we get an answer that's perfect. So we did I recollect yesterday, we did on Monday, I should say, we did an example of this shape that I'm about to draw. This is a version of question 3, right? And it's a circle, and it has x equals 0 and a line y equals x. and it's in the first quadrant. So the region D is a circle in the first quadrant, x equals 0, y equals x. Right, now if you imagine an entire circle, it would look like that. Oh, and by the way, the circle is given as x squared plus y squared equals 4. So that basically means the circle's radius 2. If you tell me a circle is in the first quadrant, that means it's here, right? Now, if I draw in the line y equals x, it looks like that. And the line y equals x makes an angle of 45 degrees that way. If I put in the line x equals 0, is the line x equals 0 that line or that line? X equals 0, vertical. So what we now have is a piece of cheese. That's the region D, and it was described by using all of these pieces here. Now, the limits of integration for r and theta are coming up. If you imagine this as being one of the lines, r starts at the origin and it finishes at the end. So it's 0 to 2. The theta is a bit trickier. The angle starts here at 45 degrees, which we turn into radians is pi upon 4. It then finishes here, and that angle is 90 degrees, or in radians, pi upon 2. Are you comfortable about how from here we drew that, and from that picture we got the limits of integration? Is there anything about, here's the story, this is what it looks like, how do you describe this using r and theta, right? We good? Okay, so what we're going to do now is tell you the rest of the question. It's a double integral over some region R or D or whatever letter of the alphabet they want to give you. That guy. Now in polar, that's going to be, for no particular reason, I'm going to do theta on the outside. Theta from pi upon 4 to pi upon 2. R is going to go 0 to 2. 4x becomes 4 r cos theta. Take away y becomes r sin theta. And the dA becomes r dr d theta. And this now becomes theta is pi upon 4 to pi upon 2. R equals 0 to 2. If I pull out an r and multiply that guy, what I end up with is an r squared, a 4 cosine theta, take away a sine theta. Now I have a dr, and now I have a d theta. So this would be the double integral, pretty much converted into polar. And again, you get lucky. Do you notice that in this question, the variables are separable and that all the limits are numbers? As long as that's the case, you can separate them. But you need both features, right? These two things must be separated and multiplied together, and the limits of integration must contain nothing but numbers, which is pretty common in these. So that means I can separate it as a pi upon 4. There we go. To pi upon 2. And 4 cosine theta, take away sine theta, times 0 to 2. of an r squared dr. Right. That's as far as I'm going to take this one, because I think that's a very simple integration, right? You're just going to get 4 sine theta plus a cosine theta, and you're going to plug in pi upon 2 and pi upon 4. And this guy here is just going to get you 1/3 r cubed is 0 to 2. So dot, 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 dot. That's the end of that one. If you're interested, according to what's in front of me here, the answer's slightly ugly. 32/3 take away 20 root 2 over 3. I suspect you're going to get the root 2s and 3s for whatever reason. Not quite sure why. Must be probably to do with the trig values. Okay. Question 4 is essentially another version of question 2. Just with slightly different numbers. Okay. Let's set up 5. Double integral over some region R. The sine of x squared plus y squared dA. And the region D, it's in the first quadrant. And it's the area between 2 circles. And the radius is 2 and the other radius is 5. So that there, and we're calling this region R this time, that's the guy that we need to do first. So first quadrant means it's in this region here. And it's 1 circle, it's a second circle. That's 2, that's 5, and we're talking about that guy. Does that look, from this description, does that look okay to you? Right. First quadrant, between 2 circles. If you imagine the entire shape, can you see the whole shape there? Can you see the 2 circles they're talking about? Now I need an R and I need a theta. Okay, anybody want to tell me what would the R and theta be? So what you might want to do is just imagine a little radial line, which is this guy here, and look at what would the values of R be when that shaded region starts, and what would the value of R be when you finish. Any takers? What is the range of R in this picture? We got one. And let's see. Yep, Thomas, it's from 2 to 5. Now, if you're interested, as we should be, what are the thetas? Can you imagine you start at the x-axis, which is theta equals 0, and you rotate and you stop here, which is at what, 90 degrees, which we call pi upon 2. So let's take this guy and see what we get. No particular reason. I'll do r's first and theta second. The sine of x squared plus y squared actually is the sine of r squared. The dA is going to be an r dr d theta. And this one is variable separable again. If you do the r values from 2 to 5, you get an r sine of r squared dr times, and the thetas go from 0 to pi upon 2, except there isn't any thetas. I think we did this on Monday. When there isn't any thetas, don't you get 1? So it's 1 d theta. Right, this guy here is dead easy to do. the answer ends up pi upon 2. What method will we use to integrate this fella? It's probably U sub or integration by parts, right? That's the two candidates. What would you use on this one? Any takers?
So the R is the derivative of R squared.
Mm-hmm.
So that's where you
So-
do your U sub.
So it's as far as I'm going, do a U sub. And it ends up being, I think it's a half sine nu when you're finished, which is pretty easy to integrate. Are we getting a little bit more comfortable about this polar conversion technique that allows you to find, well, I mean, if I bring this one back for a minute, if you try to integrate that guy with x squared plus y squared, well, for starters, just trying to describe this region in terms of x and y would be a nightmare. But if you manage to do it, you'd probably get things like x is equal to the square root of 4 minus y squared to x equals the square root of 25 minus y squared. The math would be so horrendous you would give up. But it converts really nicely, doesn't it, into polar?
I think it's much more intuitive because you actually have a picture where when we're doing the X and Y double integrals, like it's hard to picture what you're actually integrating.
Yeah, you sometimes you need to do Desmos because it's hard to to even visualize what y equals x cubed minus e to the x even looks like. I mean, who knows? Yeah. And yeah, it is hard. You're right. Okay, that's that one out of the way. Okay, I'm going to do part of 6, the start again. In this case, it's a double integral. That's interesting. It's pretty ugly. And the region R is described as the area between two circles. And one of the circles is x squared plus y squared equals a squared. And the other one is x squared plus y squared equals b squared. And then they give me a little extra help by telling me that this here is the region R. Right, so I'm going to have to try and figure out what does that guy look like. Well, it's an area between two circles. So I know the two circles are like this guy and that guy. So it's a donut shape. Right. Now that guy has a radius of A, and that circle has a radius of B. And this guy here is to tell me that the little guy is A and the bigger guy is B. So the region that we're going to do is that guy. We're comfortable with that? Area between two circles. One circle has a radius A, the other circle has a radius B. And since A is smaller than B, that means this is A and that's B. I mean, the only other choice was B then A, so I guess it's not a big choice. From there, we now need to find out what the polar limits of integration would be. I'm going to go for the easy one first. It's a complete circle, right? Inside another complete circle. Complete circles are 0 to 2 pi. Now, if you project a radial line, do you see that the radius starts at a value of A and it finishes at B? So A goes there to B. Are we comfortable with that now? A to B.
Okay. Can you hear me okay? Because
ellipses appearing here? Can you hear me at all?
Yeah, you were muffled for a second there.
Am I back to being okay?
Yes.
Right. Who knows what the earphones are up to? Right, so this represents the same thing, right? That's polar. That's the polar description of this guy up here. So we're now going to do the integral from theta equals 0 to theta equals 2 pi, and the integral from r equals a to r equals b. Now, technically, a and b are numbers, right? So that's good. Y squared is going to be r sine theta squared. X squared plus y squared is r squared. And the dA is going to be r dr d theta. Are you comfortable about all the pieces, where they're coming from? That guy is y squared. That guy is x squared plus y squared. And the r dr d theta basically does the dx dy part. Now I'm going to do a little tidying up. If you multiply this guy out, you get r squared sine squared theta over r squared times r dr d theta. These two cancel. And we're going to have theta from 0 to 2 pi again. And r equals a to r equals b again. And sine squared times r. It's kind of nice to put the r in the front. Variable separable. So it's going to go 0 to 2 pi sine squared theta d theta. And from r equals a to b of a single r dr. Right, so variable separable seems to be pretty much every question so far, which doesn't surprise me too much. Right, let's do that one first. Power rule, evaluated at r equals a to r equals b. That's going to get me 1/2 b squared, take away 1/2 a squared. And we're done, right? That was quick. Okay, now we have trig. This is sine squared on its own. And what I'm about to do, you will also do it with cos squared on its own. And God forbid you ever get a sine squared cos squared, because that's one of these really horrible ones I was talking about before. That guy gets changed. He gets changed using a trig identity. And somewhere, when you were doing Calc 2, you discovered or used the identity that sine squared is the same thing as 1/2 1 minus cos, and I forgot my 2 theta. Do you remember that guy? Now the other one, very similar. Cos squared theta is 1/2 1 plus the cosine of 2 theta. So this guy is now going to be 0 to 2 pi, 1/2, take away 1/2 cosine of 2 theta d theta. Integrate 1/2, you get 1/2 theta. If you integrate a cosine of 2 theta, you will get a sine of 2 theta times an extra 1/2. And then you can evaluate it at theta equals 0 and theta equals 2 pi. You get 1/2 2 pi, take away a quarter of the sine of what, 4 pi? Minus 1/2 0 is 0. Take away the quarter of the sine of 0. Times all of that stuff. Oh, by the way, now that I've done this, do you know that the last time I got one of these, I did both of them separately, then I could write the answer. Do you see how it would have probably been better to do this one separately and do that separately, and then just at the end put one answer? Otherwise, I end up having to write the same bloody thing 5 times. Right. So you might want to do this guy separate, and then just stick the answers at the end. But committed. That times that guy gets you pi. The sine of 4 pi is 0, so pi take away 0. Minus 0 and 0, take away a whole load of zeros. So after all that hard work, looks like that. Pi is all that's left here. I'd probably put a half as a common factor. And that's the answer. And the good news is it's right. Okay. I think the hardest part here is just referring back to the sine squared is not a use-up. It's use an identity, convert it into something else that you can then integrate. Okay, how are we doing? Any questions?
Do you ever use your trigonometric forms, the table of integrals? Or because I noticed that since I've been taking calc at Olympic College, no one's ever mentioned those tables.
I'm trying to think of what you mean by those tables. I'm not sure. You mean there's a whole load of integrals that you could just go looking up?
Yeah, so if you
standard go integrals.
Yeah, if you go to the back of the book, there's a bunch of them already listed.
The only, I know exactly what you're talking. The only time that we would actually use them would be for non-standard integrals. So if somebody went and said to me, integrate secant cubed theta, which I couldn't do, or integrate secant theta, then I would probably go and look at them in those questions. In a test or an exam, if I gave you something weird like secant theta, I would just tell you, oh, hence the integral of secant theta is the natural log of secant plus tan. I think that's what that one is anyway. And you would just use it. So if you're doing your homework, of course, you could probably save yourself a little bit of grief, I guess. Although some of these are not written down as an answer, that one probably is. A lot of them are written down as recursive relationships, so you still have a whole load of work to do anyway. So you might as well just use sub it and call it good. It's good practice to do use subs because of the number of different situations where they come up. Okay, where are we going with this one? Yep, done one like that. 8 is kind of the same idea as, you know, one of the questions where you do that again. So that's what 8 looks like. Oh, 7 is different. I can do 7. Question 7, at least one like it. It's e to the negative x squared negative y squared, dA, in the region R. And the region R is described as this guy. So it's bounded by this curve and the y-axis. So the region R is bounded by this thing and the y-axis. It's probably not the most intuitive way of describing this region. So here goes. I know it's the y-axis, so that guy is going to make up one piece of the shape. this horrible mess here, this bit, might not look like, it might not look like what it is, but if I square both sides, and then I add y squared to both sides, do you see it's just a hidden circle? Are we cool? Now, if you put one extra piece of information, which again is not obvious, do you notice that this square root is positive? Right? It's not negative, the square root of this, it's positive. That means the x's in your circle must be positive. So when I put these two together, do you see all I get is that half of a circle? I mean, it probably would have been easier if I just said the right-hand half of a circle, right? Because that's essentially what we've got. Are you okay with that? That this, along with that, essentially is the right-hand half of a circle, and the y-axis is just emphasizing that. Now I'm going to do the R. Oh, by the way, the radius of that circle is 7. Do you agree? 7. Now, if you want to do the limit of integration of the R's, you just pick a random radial line. And can you see that in this case, the R value is 0 and it's still inside the shape until you get to 7. So that tells me it's 0 to 7. And now we're going to have to think a little bit harder about the range of values for theta. See, normally, at least in all the other ones we've done, you start with the x-axis and you kind of build it this way. Now, if I start at the x-axis and I build it that way, well, at least I can tell you what this piece is, but I don't get to tell you that piece. And you can't just say, well, can't I just keep on going until I hit that piece? Well, if I do that, I'm actually describing the whole circle. So what I'm going to do instead is I'm going to say, okay, what would that movement be? Well, you'd start at negative 90 degrees, negative pi upon 2, and then you'd end up here at positive pi upon 2. You got that? Negative pi upon 2 plus pi upon 2. So negative 90 degrees to plus 90. Okay, that one's a little bit sneaky. Are you happy about the polar version of this shape based on the theta and the r? Any issues? Call it good. Okay. R is going to go from 0 to 7. Theta is going to go from negative pi upon 2 to positive pi upon 2. Ah, okay. This guy is not as ugly as he looks. He turns into polar quite nice. Forget about the E for a minute. If that was x squared plus y squared, wouldn't that be r squared? Since it's negative x squared, negative y squared, doesn't it negative r squared? So what you get here is e to the negative r squared. And then you get your r, in this case d theta, dr. And I have variables separable. I have that piece. And when there's no thetas in town, you still get 1. That integral is dead easy. It ends up being pi. You can check it out. And I hope you would look at that and say it's a u sub and u is negative r squared. You agree? U sub u equals negative r squared, and you're done. Yeah, that one's pretty straightforward. Don't worry about that. Okay. Let's just show you the last two. We'll just talk through those ones, and we will have basically done polar. Right. I think it's let's look at 10 first. It says evaluate this integral by converting to polar coordinates. Right. What you can't see there is what the region looks like. If I write down this and then I'll come back and show you y equals 0 to y equals 6, and I'll do that again. X equals 0 to x equals 6, and then y equals 0 to y equals the square root of 36 take away x squared, and then they have some stuff, right? Actually, I think I'll just look at that one right now before we get too far ahead of ourselves. Right. If I'm going to turn that into polar, I need to know what the region looks like so I can describe it in terms of r and theta. And right now, it doesn't look like you can tell much at all. So let's try and reconstruct this region in terms of x and y. If you take y equals the square root of 36 take away x squared and you rearrange it, can you trust me you end up with that guy? So isn't that just a disguised circle? Great. Now, it's a positive square root. So you're telling me that y has to be positive, and that makes you only that half of the circle. And that circle goes from -6 to 6. So if that's the only thing you told me, that would be my shape. But then you tell me here that the x's go from 0 to 6. And if you look at the x's going from 0 to 6, do you see that the region now just ends up being that little guy? Now, that's the region you're good to go. So you're going to go R, well, do a radial line from 0 to 6, and theta, a pretty standard theta, 0 to 90 degrees, which is pi upon 2. So we would do the integral from r equals 0 to r equals 6, the integral from theta equals 0 to pi upon 2. I've just did that a few moments ago. Isn't that e to the negative r squared times r dr d theta? Can you see that's almost a carbon copy now of the previous question? So I'll leave that one as is. In the next question, it's really a duplication of this kind of information. So suppose I give you y equals 0 to y equals a, and I give you x equals negative a squared take away y squared to positive a squared take away y squared, and then whatever function goes here. The first thing I'm going to do is figure out what does this region look like. If you rearrange this guy and you rearrange this guy, you get the same thing. It ends up being a circle, radius a. So if you rearrange that one and you rearrange that one. Now, since the x is positive and the x is negative, right now that means it's a whole circle. And the radius is a. If you then factor in y equals 0 to y equals a, then it's not going to be the whole circle anymore. If y equals 0 to y equals a, doesn't that mean that it has to be only the top half of the circle? So that's the region. This guy basically tells you it's a circle, and this guy helps tell you what bit of the circle you're going to use. And in this question then, the r is 0 to a, and the theta is 0 to pi, and then off you go. Are we good on that? Right, and give me a little few moments to sort some things out. And we'll be starting our final section. I had a question that I thought I'd deleted, but evidently I hadn't. So now I'm doing it. Right. Who's the next guy? It is 15.4. I'm going to deal with applications. Really, they could have probably just called it centre of mass, because almost every question except the first one is centre of mass. And if you're into engineering and boats and aircraft and things, the centre of mass is a very important thing. It's basically a 1 point on a, in our case, in a two-dimensional space that represents like the balance point. So if you've ever done any kind of, I think it's in mechanics that happens, right? Can you imagine that I've got just a nice basic rectangular plate? And we talk about what's called a density function. So any given value of x and y, this plate might weigh differently. Can you imagine that at this end it's much heavier and at this end it's lighter, right? So the density function just tells you the density at any given point xy. Let's suppose that this plate was a constant density, right? So no matter what part of the plate you're talking about, it weighs, 6 pounds per square foot, right? That would be a density unit. And if I insert into this the x and y coordinate system, if I drew this thing well, hope I have, wouldn't the orange be the origin be the center of mass? Now, if your shape happened to be, say, off center, as a rough guesstimate, wouldn't there be the center of mass? And we use notation x bar, y bar to represent the x and y coordinate of the center of mass. So when you're finished, your answer is going to be the center of mass is 5,4. The center of mass is pi upon 2, 0, right? You're going to tell me coordinates. So how do we find this magic x bar, right? The x coordinate of the center of mass, and the y bar, right? The y coordinate of the center of mass, for a function where the shape, in this case, my shape is D, right? That whole thing there represents the region D, that has a density function. So can you imagine it gets much more complicated when the plate is not got the same density, right? At one end, it's much denser, heavier, right? And at the other end. And we describe density functions by functions that might look something like this. That density function would tell me that if you know the x and y coordinate of the point, the density at that point would be x squared plus y squared. That would be a shape that gets heavier the further away from the origin you get. That would be an example of that. So the general method is over here. The center of mass for any given function, any density function, rho of xy, over some region D is called x bar, y bar, right? It's a coordinate in 2D space. If you imagine, what's this? Can you imagine this guy being that rectangle I'm talking about? Maybe over here there's a lot of weight, right? And over here there's nothing, right? It's a boat that's had a lot of stuff stacked on this side and there's nothing stacked on that side. Can you see that the center of mass wouldn't be there? It'd be probably here, right? Closer to the end. So, x bar is 1 over m this integral. Y bar is 1 over m this integral. And m is essentially the total mass of the object, right? So that would be, what does this block weigh, right? That's m. And you get the total mass of an object by integrating its density function over the region D, whatever it's described as. We okay? Density. So let's find some density functions. Well, actually, we're not going to do a density function as our first one. Everything else after that will be a density function. We're going to do one question, one application that's not. So let me zoom over and show you what that guy looks like. Okay, so in the first question, which isn't a density function after all, is that the electric charge is distributed over a rectangle, and the x's go from 0 to 4 and the y's go from 5 to 8. So it's some kind of rectangle in the top right hand corner, and its density, or in this case its charge density, is given by 6x add 4y. Find the total charge. If you find the double integral of a density function, you get its mass. If you find a double integral of a charge density function, you would get the total charge on that plate. If you take any object and you describe some property, can you imagine that you might be able to do, talk about one. Can you imagine you might do a plate where it has different temperatures at different points? So you imagine I've got a rectangular plate, and at this end here, it's really hot, and then towards the edges, you know, it gets cooler. Then you might have a thing called the temperature density function, and I'm just going to call it rho, and it might be simply just 5y. Might be 5x plus 5y. If you do a double integral over this region of that guy, what you're getting is the total temperature energy, right? The amount of heat energy you would get in that plate. So in the one that we just did a few moments ago, you would do a double integral from x equals 0 to 4, and from y equals 5 to 8. And the function you're going to be doing is that guy. And then you could do a dy dx, and that would be the integral that you'd be getting. Right, that's your region, that's your density function, there's your variables. Yeah, I'm going to be leaving this virtually here, but let me talk a little bit more about what would come next. I know these are both numbers, which is great. Is this function variable separable? No. So wouldn't you just have to do the dy's first and then later on do the dx's? There's no avoiding it. Okay, let me now return to the next question, which is basically what all the others are going to look like. And it's this guy. This figure shows a flat plate, a lamina, that is shaded according to its given density function. And can you see that this function is much denser as x is big and not very dense at x being small? And we're being asked to estimate, actually to calculate, the center of mass. Now, if you're being asked to estimate it, if it was equal density, wouldn't roughly a half comma half be a good idea? If the plate had the same density all the way through, roughly where my mouse is, which is a half comma half, since it is more dense than that, I would probably go 3/4 comma and a half. What are you going for, John? 2/3. Okay, 2/3 seems good too, right? Definitely the x's would be bigger than a half. The y would be a half, wouldn't it? Because vertically the density is the same. So the y is probably going to be right in the middle, the y value of a half. Okay. So we're going to set this whole story up and let's take you through it. The process, thankfully, is pretty standard. So once you've done one, you've pretty much done them all. So I have a density function to work with, and it's x cubed. And I have a region, which is a very simple, that guy, right? So first thing you do is you calculate m, because you're going to use it here and here. M is the integral of this region, so that's going to be x equals 0 to x equals 1, y equals 0 to y equals 1. The density function, in my case, dy dx. Now, you want to make life easy. Would you agree that this one is variable separable? So, to get the total mass of this plate, you would do from 0 to 1 of x cubed. And when you don't get anybody, you always have 1. This guy is a power rule. And this guy's dead easy is 1. You know, you can check it out, but he's 1. And this guy, well, he ends up being a quarter. So a quarter times 1 gets you a quarter. So the total mass of this is a quarter. Now, to get x bar, I use this formula. That'll be the x coordinate at the center of the mass. And y bar is going to equal this guy, right? So far, so good. Now, I can save myself a little bit of time by predicting one of the two centers of mass without calculating. Do you notice that the density function only has x's in it? So that means that the y value has no effect on the answer. And since the y value has no effect on the answer, my prediction is y is going to be a half. Does that seem reasonable? Or y bar, I should say. It's going to be a half. If the function only has y's in it, right? Let's say the density function is y squared plus y. If that was the case, won't x bar be halfway between 0 and 1, in which case x bar would be a half? Now, if you can't see that, then just do the math. You'll come up with the same answer, right? It will end up being what we predicted. So, moving on then, I now want to find x bar. So it's going to be 1 over the mass, well, 1 over a quarter, right? The double integral of x, the density function, dA. So 1 over a quarter gets me 4. the region that we're talking about is x equals 0 to 1, y equals 0 to 1, x times the density function, which just happens to be x cubed, dy dx. Tidy that up a little bit. X equals 0, x equals 1, y equals 0, y equals 1, x to the 4. And everybody is happy because it's variable separable. So it's going to be 4 times the integral from 0 to 1 of x to the 4 times the integral of y from 0 to 1. Yeah, that guy. This guy is 1. This guy is 1/5 x to the 5. And that fella ends up being essentially a 5th, take away 0. Well, I think, John, you said 2/3. A pretty good guess. 4/5 is maybe a little bit bigger than that, but it's in the ballpark. For completeness sake, will you just trust me that the answer is a half? But if you don't trust me, do that calculation and you'll find out it's a half, okay? And so the center of mass of this shape is 4/5, 1/2. And good, I've just checked, it's the right answer. So you're going to get this guy, which is basically a double integral. You're going to get these two guys, aren't they just slightly different versions of this double integral? And then put them together, you've got an x bar and a y bar. And if you can see any shortcuts like, well, I'm pretty sure x bar is 0 or x bar is a half, then do it. Saves you some work. As long as it's a correct prediction, you should be fine. Any questions before I tackle the next one? Okay, here it goes. Suppose I tell you that the region D is given in this format. And that the density function is given as ky squared. And you might think, oh God, what's this k going to do? I want you to think of this k as a constant. It's just a fixed number you don't know. That's all it is. And if I draw my little picture of D, it really is x goes from 1 to 4 and y goes from 0 to 4. So basically, it's that guy, agreed? Now, the density function here has nothing but y squares in it, agreed? That means the x's don't matter, right? The x's have no effect. That means I can make a prediction. Won't x bar be 5/2, right in the middle of 1 and 4? Right. If this function had been that guy, or for that matter, that guy, if that had been the density function, wouldn't the thing be the y's don't matter? Right? There's no y's in it. The y's have no effect in the answer. Wouldn't y bar be 2? Do you see how that saves you half the workload? Right? If you get now, if the density function has x's and y's in it, you're going to have to calculate everybody, right? There's no obvious shortcut. But if it only has y's, you can predict the x bar. If it only has x's, you can predict the y bar, provided the shape is something like a rectangle, right? You can figure out the middle of a rectangle easily. So the mass then is the integral from x equals 1 to 4 y equals 0 to 4 of the density function dy dx. And oh, I can do a variable separable. There's the x. And there's my y. If you integrate this guy, you get x. X from 4 to 1 gets you 3. That's how I can do those ones so quickly. If this is a 1, the answer is just the difference from the start to the finish. So if this was 0 to 20, that would be 20. Right? If this was 1 to 40, that would be 39. Now this guy, you do have to do work. You add 1 to the power, and you divide by the new power. Evaluated at 0, and evaluated at 4, and that's 64 thirds. Oh, they cancel, so the answer is 64. Okay. I just cut some lines out, right? Plug in 4, get the answer, take away 0. 4 cubed is 64. 64 thirds times that, the 3's cancel, 64k. I have got 1/2 of my answer. Now I only need to find the y bar. So the y bar is going to be the integral from x equals 1 to x equals 4, from y equals 0 to y equals 4. And the formula is y times the density function. So y times ky squared. And I forgot my 1 over m thing. So it's going to be 1 over 64k. And this guy can be rewritten as ky cubed. So I'm going to save some time and realize that it's a variable separable. And you're going to get a ky cubed. This guy is 3. And this guy is add 1 to the power and divide by the new power. Evaluated from 0 to 4. If you plug 4 into here, you get 4 to the power of 4. That gets cancelled out by one of these, so you get 4 cubed. So you get 64. Okay. And I wasn't expecting such a nice answer. Did you notice that after everything, that the answer is just 3? Because wouldn't that cancel with that? And you've got 3. And I already know what x bar is. Right, we did it as a predictor. And so the center of mass would be 5 over 2, comma 3. Now, if you look at this picture, the guy with coordinates 5 over 2, 3 is about here, right? He's quite high up. But isn't that caused by the density function saying it's really heavy on the top and lighter down at the bottom, right? So I would expect that the answer to the center of mass was further up than the middle, right? Which is 2. It happens to be a height of 3. And have you noticed that the k disappeared in the x bar and y bar? That will happen every single time. So if you do an x bar and a y bar and you think one of the answers is 3k or 5 over 2k, you've made a mistake somewhere. The k's disappear. Which is kind of interesting that that's the case, but they do. Any questions about the one we just did, which is similar to question 3?
There must be a really big application in this in buoyancy.
I think people who, yeah, I mean, this is a very primitive shape, but you can imagine stacking containers. You might want to know where the center of mass of a container is, because if it's far too high and the wind blows on the side, won't that thing keel over? And on buoyancy, if you're doing ships, don't you want the center of mass? If I do a very bad ship, right, imagine that's a ship out of water. If you want to be really stable, right, so you don't have a ship that's digging into the water as it sails forward, right, or is susceptible to other movements, what you want for a good center of mass is you want it to be roughly in the middle, and don't you want it to be as low as you can? That's a stable center of mass. If I had a center of mass that's up here, right? Imagine that's an aircraft carrier. My center of mass is up here. That is not going to be good, because you imagine winds blowing this. Isn't there a tendency for it to go that way? I don't want a center of mass up here, because as you sail through the water, isn't the bow going to dig into the water? You're going to have a hard time moving. And if it digs in too much, you might even have instabilities. If you're doing an aircraft, and again, I can't try to save myself. If you do an aircraft, you want the center of mass to roughly be between the two wings. That is the most stable place to have a center of mass for control purposes, right? If you have your center of mass too forward, aren't you going to have an aircraft that's kind of fighting to go down? And if you have it too far to the back, won't it go up? And isn't that when they load aircraft, they are very careful about, you know, where you put stuff. If you have a ship and then you put those weird containers that they love to put on container cargo ships, I have seen some of them, which is totally scary to me, because the minute you put those guys in, aren't you going to raise the center of mass of your ship? And if you put too many of them and the containers are stacked badly would be putting the heaviest on top and the lightest ones underneath. So that would even make it worse. Couldn't you have a center of mass that is so high that that ship would be totally unstable in any kind of rough sea? You would definitely get some keeling over one way or the other, which I have seen happen, but that tends to be when high winds blow against it, right, which is more likely to cause a problem than a typical sea, because they're so massive, these things, that their natural weight would reduce the chances of stability. But when wind hits it, it now becomes a totally different story, because that's basically a big sail. And if you've got a wind pushing it, it's going to go that way. So yeah, buoyancy is a big one. But buildings are the same. You want a center of mass of a building, to be in the middle of the building would be definitely a good idea, and as low down as you can get because of crosswinds. Okay, let's pick another fella. A lot of these questions, I'm just going to set the integral up, the region and the density. In question 4, the density function is 9x add y. That means I'm going to have to find x bar and y bar. There's no shortcuts. Secondly, the region is described in terms of a triangle, and they give me the coordinates. So let's draw the region. 0, 0, 2, 1, 0, 3. And that's my region D. Now, if you want to describe this region, we have to do it in terms of x's and y's, because there aren't any circular things going on. And we have a choice. Do I go vertical, which would be 0 equals x equals 0 to 2, go that way, or do I go horizontal? Well, I think in this case, isn't vertical the way to go? So I know the x is from 0 to 2. That's the easy piece. And I need to know the equation of this line. Well, it passes through the origin and its slope is a half. So there we go. And I need to know the equation of this line as well. And what do I know about this line? Well, if you do rise over run, it's got a slope of -1. And since it passes through that guy, it's 3. So I'm taking the shortcut to get the equations, but there are other ways. Couldn't you just find the coordinates of the start and finish, get the slope, y minus y1? Right. In the one that I've just described then, the big guy is this fella, and the lower guy is this fella. So that's one problem solved. That's the limits of integration. So to get the mass, it's going to be the integral from x equals 0 to x equals 2. And there we go. And from y equals a half x to y equals -x add 3. The density function is that guy, dy dx. And there is no shortcuts. There are no variables separable. You just have to do that the usual good old-fashioned way. Let's pretend that that answer is 2. I know it's not, but let's pretend it's 2. If you wanted to, for instance, get x bar, it would be 1 over the mass, 2. The same double integral as we have up here, at least the limits are the same. And the only difference is you add for x bar an extra x. Now, if I want to integrate this guy, I would strongly suggest that you do a bit of work with him. And what I suggest that you might want to do, in fact, you might want to do it up there as well, is multiply it all through. And that gets you 9x squared plus 9y. 9x1. So that integral will get you x bar. And this integral up here, I would do that to it. That guy will get you the mass. Okay, so it's about halfway through these guys. Set up the next one. In this case, the region D is a triangular region, and it's described by y equals 0, y equals 4x, x plus 4y equals 1, and the density function is x. Now, I wish I could tell you, oh, this guy is x. Since he doesn't have y's, then I should be able to predict the y bar. You can only do that if the regions are rectangular, right, or a circle. You can't use it in mixed versions like this. Now, this equation here is just ridiculously ugly because it's not really helpful. So I'm going to rearrange it as that guy. And now I'm going to try and draw it. I would probably actually do it in Desmos, but I'm going to do it here on paper. And y equals 4x is basically a straight line. And y equals 1/4, take away that guy. And can you imagine this is a quarter? I can make my scale anything I like, and it goes down that way. And this is what y equals 1/4, take away 1/4 x looks like. They also have y equals 0 going on here. And what is y equals 0 except the x-axis? Now, when you put the x-axis in, do you see that the triangle they're now talking about is that one? Right, two straight lines and the x-axis. So I'm looking at this guy and I want to set it up, right, using limits of integration for x and y. And I always have two choices. I can do vertical, right, going this way, or I can do horizontally, going that way. If I try to do vertical here, would you see I'd have the x-axis in one line and then a switch over and the x-axis on the other line? I think John mentioned on Monday, could we split it into two and do it that way? Yeah, I guess you could, but doesn't that double your workload? So in this question here, I think going horizontal is just so much easier. Of course, I will need to know the coordinates at that point. And if I had Desmos in front of me, I'd be able to click on it and it would tell me. But since I don't have Desmos in front of me, let's see what it would be. I'm trying to solve when y equals 4x intersects that guy. Well, to do that, all you need to do is find out the coordinates, the x coordinate, if you like, where that happens. Well, if I add a quarter x to both sides, 4 1/4. Oh, you're not going to, yeah, you are. I just looked at the answer. You're going to get me 17 quarters x equals 1/4. Okay, 4 1/4 is 17 quarters. And then if you, I don't know, if you multiply both sides by 4, you get 17x equals 1. And so x is a ridiculous number. That guy there is 1/17. And the y value is 4 of them. So this guy up here is 4/17. I'm not sure Desmos would handle a fraction like 4/17. Desmos might just tell you it's 0.2833 or something weird. So I'm ready to set up my limits of integration. We're going to go y value. So it's going to start at 0 and finish at 4/17. And now the x's. Well, yeah, life is never straightforward. I need these equations of these lines to be rewritten as x equals a function of y. So this guy, if you divide both sides by 4, you get x is a quarter y. And this guy, if you probably start here is easier, you can get x is 1 minus 4y. Right, that one rearranged in the format x equals. And now I'm left with just one more decision. One of these lines goes here, and the other one goes here. Right. Big guy goes here, little guy goes here. And if you look at this fella, isn't the big guy him? Furthest to the right. So this side is 1 take away 4y, and this side is 1/4 y. And that work was only to find the region D. So we can calculate the mass now as the integral from y equals 0 to 4/17, and from x equals 1/4 y to 1 minus 4y. And the density function, thankfully, is just x. Then it's going to be dx dy. And whatever that number is, it goes here. Whoops, what's this? Goes here to get dx, x bar, and it goes here to get y bar. And if you're going to do x bar, you take this guy and what you add an extra x, so it'd basically be this integral with an x squared. And if you wanted this one, you'd multiply by a y, so you would get this double integral xy. The only extra bit is remembering 1 over m in both cases, and that would be it. So still a lot of work to do in that one. It's probably why there's only 8 questions. How are we doing, guys? What is this? This is 80 minutes into the day. How are you doing? Or 100 minutes, actually. We good? Any questions before I tackle the next few? Okay. Got about 2 more to do. Call it a day. Okay, inversion. Eversion of question 6. The region D is bounded by a curve and this guy. And the density function, okay, it's another one of those guys with a K in it, but we've dealt with the K, so that's not such a big deal. I want to draw this picture so that I'm clear in my mind what it looks like. 1 minus x squared. I'm just going to stop talking for a few seconds. John, have you got a joke for me?
No, I'm not.
Thomas, have you got a joke for us? I know Sarah has. She's always got jokes. No jokes, Thomas? Sarah, get me out of this hole. Have you got a joke? Nobody. Yeah, okay. 1 minus x squared looks like this guy. When you tell me y equals 0, that's the x-axis. So actually the region is pretty straightforward. It's just that bit. The limits of integration. I think this is a pretty obvious candidate for going vertical, which means that the x's will range from -1 as you scan to the end +1. And the y values, which is the bottom of the rectangle to the top, start at 0 and finishes here, which is at 1 minus x squared. Actually quite straightforward, that one, wasn't it? It wasn't really too much to do. So if I want to get the mass, it's going to be the integral from x equals -1 to x equals 1. It's going to be y equals 0 to y equals 1 minus x squared. The density function is 11 ky dy dx. And whenever you get a double integral where one of the limits of integration contains a variable, you're never going to get variable separable, right? You just have to do them the long way, 2 at a time. So let's do this one, see what we get. It's going to be from x equals -1 to x equals 1. This guy. Well, if you integrate 11 ky with respect to y, you're going to get 11 ky squared, add 1 to the power, divided by 2. We're comfortable with that? 11k, the y comes 2, divided by the new power. Evaluated at 0 and at 1 minus x squared dx. So it's going to be the integral from -1 to +1. If you replace this y by that guy, you get 11 over 2 k 1 minus x squared squared. Take away nothing, so I won't bother about it. That guy. Now this integral needs to be fixed. Oh, here's a little trick for you. If you have got constants that are just a pain in the butt and they're getting in the way, you can bring them outside the integral as long as they're numbers and just focus on that guy. And if I FOIL this guy out, I get that guy. And that saves me not having to deal with 11k over 2, all over the place. So if there is a fixed value, a constant, you're allowed to pick it up and stick it outside the integral. Now that means that once I'm finished with this integral, I still have to remember to multiply it by 11 over 2k. But at least that's not as hard as dealing with it all the way through every calculation. Now this guy is x. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Evaluated at these two extremes. Okay, you plug in 1, plug in 1, you plug in 1. If you plug in -1, if you plug in -1 here, you get -1 because -1 cubed is -1, but that's also negative, so you end up with +2/3. And if you plug in -1 here, you get -1 to the 5th, which is still -1, and so you get -1/5 here. And just being lazy, I get that guy, take away that guy, add that guy, take away a negative means you add it, take away that guy, and take away that guy, you add it. So basically you get this stuff, and let's see what that comes out to be. I should do it in a calculator, can't I? It's the easiest. That's 2, take away 4/3, add 2/5, and turn it into a fraction, and 16/15. Okay. And that guy times that guy, they're a little bit of cancelling, but not much. You get 88/15k, and that's the M. Right. That times that, 88, 8 times that's 88/15k. And that's that guy. And then to get x bar, you do virtually the same integration up here, right? But with a 1 over m, which is 1 over that ugly guy, and multiply this thing here by, wrong place. Multiply this guy here by an extra x to get x bar, and multiply this guy here by an extra y to get the y bar. And according to the answer that is in front of me here, you get 0.47. X bar is 0.47. So I'm not arguing about the 4/7. I want to find out why I could probably save some work here. Would you agree that the density function has no x's in it? Great. Would you agree that this shape, x equals 0, is exactly in the middle of it, as far as area is concerned? I should have been able to predict x bar as 0 without doing any work. But if I'd done the work, it would still come out as 0. Right, so there are 2 questions left. Both are pretty much the same question. So you're going to be doing, let's do 8 as a version of this. A lamina occupies this fella. And it's in the first quadrant. That's the easy part. The density function's still to happen. This thing basically represents an entire circle, right? But if you do it in the first quadrant, that means that only this piece represents D. So far, so good? That's D. Now, if I see a shape that has a region that is part of a circle, wouldn't it be a good idea to go polar? So I'm going to describe that in polar coordinates. So I know that the R is going to be from 0 to 7. And I know that theta is going to go from 0 to 90, which is 0 to pi upon 2. So I'm going to convert the region D, which is this guy, and I'm going to use polar. Now, here's the extra piece. The density function is described as proportional to the distance from the origin. Right, well, I mean, some of you know the language of proportion. If I tell you that a function or a thing is proportional to the distance from the origin, then I need to know what the distance of any point from the origin is. So you can imagine that's the point xy. Its distance from the origin is that distance there. And I know that distance is the square root of x squared plus y squared. So far, so good. My density function is proportional to that guy. So it's k times that guy. Now, hopefully some of you have done in physics, that's where I'd expect this to be proportion, right? It's proportional to x, it's proportional to x cubed, right? It's proportional to the velocity squared. Oh, we got some chat. Oh, thank you. Sarah did give us a joke. And Thomas, no. Right, what's a frog's favourite part of calculus? John, you got to be my foil here. What's a frog's favourite part of calculus?
Yeah, I read it. It's pretty funny.
It is. Okay. Right. Are we cool with this one? Right. Now, if I'd said the density function is proportional to the x coordinate, then kx. If I said the density function is proportional to the y coordinate, ky. If I said that the density function is proportional to the square of the distance, it would be k x squared plus y squared, right? And so on and so forth. This is the density function for our story. So what do we have? We have r goes from 0 to 7. Theta goes from 0 to pi upper 2. And the density function is k times the square root of x squared plus y squared. And this is where things get nice. Isn't square root of x squared plus y squared ki? So to get the mass, it's the integral from r equals 0 to r equals 7. It's the integral from theta equals 0 to theta equals pi upon 2. The density function, times r d theta dr. Do you see how I almost screwed that up? when you do polar, don't you always have an r dr d theta, or in this case, an r d theta dr? So we are going to be doing 0 to 7, 0 to pi upon 4 of kr squared d theta dr. Is this variable separable? Is this integral variable separable? Yeah. Does it have the features? Are both limits of integration numbers? Check. Is the function two things multiplied? One got r's, the other doesn't, right? That kind of thing? Yes. So in this case, it's going to be r equals 0 to r equals 7, kr squared dr, times theta equals 0 to theta equals pi upon 4, 1 d theta. I can tell that answer is going to be pi upon 4. And I can do this as add 1 to the power, divide by the new power, evaluated at 0 and at 7. And I have no idea what 7 cubed is, but I guess it's going to be some really ugly number. So let me try it on my calculator. If you do 7 cubed, yep, 343. So 343 k over 3, take away nothing, times pi over 4. And so the mass would be 343 twelfths with a pi and a k. Just ugly, right? It's just ugly. Now, won't finish it, but to get x bar, I'm just going to call it 1 over m, so I don't have to write that. Basically, if you turn it upside down, that's what 1 over m would be. The integral would still be from 0 to 7, and it would be x equals theta to pi upon 4. That would be an x times the density function. And I'll keep the r d theta dr guy going just for a minute. So it would be from 0 to 7, from theta to pi upon 4. This time x would become r cos theta. The density function we already calculated is k times r d theta dr. I'm going to write that guy down up here. 1 over m. R goes from 0 to 7. Theta goes from 0 to pi upon 4. And if you multiply all of this together, you get k r squared cosine of theta d theta dr. And then, hey, take what you get. At least it's variable separable. So it's going to be whatever 1 over m ends up being. The integral from 0 to 7 of kr squared times the integral from 0 to pi upon 4 cosine theta d theta. And according to WebAssign, something really interesting happens. The x bar ends up being 56 fifths, or 56 over 5 pi, comma, 56 over 5 pi. So that's x bar, y bar. And what's interesting to me is they're the same guy. And then if I go back to my picture and I think, how could I make that prediction before I did it? Well, if you think about a line that goes right in the middle, like there, wouldn't the two pieces be perfectly matched? And so the center of mass is probably going to be somewhere in that line. And if you're in that line, by the way, that line is y equals x, right? Aren't the y and x coordinates going to be the same? So I might have been able to predict that. In which case, if I found x bar, I would write down y bar as the same number. I'm not sure that intuitively that's obvious, but now that I've seen the answer, it's a lot more obvious than it would have been before I did it. We good? So imagine the same density function. Everything else is the same. The only difference I'm going to do is that the region is now that guy. So if the density function is the same guy, but the region is now this guy, I can predict x bar. What number would x bar in this story? It might not be the same in a different story, but in this one it is. Any takers? Can you imagine that that vertical line cuts the shape into two equal places? And since the density function is a measure of how far away from the center you are, it might be reasonable to assume that x bar would be 0. And it is.